My name is Amin Shukri. I am the Dean of the Electronics, Communication and Computer Engineering School at EJUST. Probably some of you have been introduced to EJUST during this conference. EJUST is a university which is called Egypt-Japan University of Science and Technology, and it is at New Burg Al Arab City. Currently, it is only for graduate studies, but by next year, hopefully, we'll start undergraduate studies. Our session today is about robotics and biorobotics in life sciences. I am not specialized in biorobotics, but I am more oriented toward artificial and computational intelligence. But I was happy today in the previous session to hear people talking about many things related to artificial intelligence, computational intelligence, machine learning, and so on. I am supposed to introduce the session in 5 minutes, so I don't want to talk a lot, but today we have 3 main speakers. Dr. Frank Roffer from CNRS, it's Centre National de Recherche Scientifique from France. I am happy to receive him here because I got my PhD from France also. We have the second speaker is Dr. Nikolaos Mavridis. Unfortunately, he couldn't be with us today, but he sent a video which we will see together. And the third speaker is Dr. Victor Park. He is assistant professor at Waseda University, Japan, and he is also an adjunct professor at EJUST. As I told you, I'm not specialized in the topic, so I have tried first to precisely define what is biorobotics. So here, it is about bringing biology and robotics together. So let us focus a little bit more. Since the birth of AI, there was always an interaction between engineers and biologists. The engineers tries also always to copy from nature. This means to understand how animals, living organisms, living beings, how they work. This is in order to construct machine, or let us say biologically inspired robots. On the other hand, as in AI, the biologist part, or in AI, the cognitive side of AI, tried to use the computer as a model, or as a tool, sorry, to understand mind processes. So here in biorobotics, the biologists try to benefit from the familiarity of engineers with complex artificial systems in order to understand and recognize better the structure, the function, the operation of complex biological systems. And finally, and hopefully, to use robots to solve problems in biology and medicine. So this idea of studying man and machine, or human or living organisms and machine, is as old as the 40s of the last century, where Norbert Wiener coined the term cybernetics. Cybernetics was concerned about studying control and communication in animals and machines. Maybe you know that even the computer, the first digital computer, was constructed by this time. In the 40s, the first computer, electronic digital computer, was ENIAC. It was constructed at Pennsylvania University. So all the concept studies were about learning, adaptation, cognition, communication, sensory motor in animals and machines. Of course, there is many applications, and the remainder of the slides is about many things that maybe that have been presented today. So I will bypass this and give time to our next speaker, Dr. Frank Ruffer. I hope that I pronounce it well. So Dr. Frank will introduce us to vision and bio-inspired robots.
Yes. So thank you very much for the introduction. So my name is Franck Ruffier. I'm come from ex-Marseille University and CNRS at Marseille. So I'm co-heading the lab of biorobotics in Marseille. Thank you. So I will speak about biomimetic vision and bio-inspired robots. Okay, sorry about that. Great. So in the lab, we are very interested by such animal. For example, here, another fly that is able to maneuver very closely to obstacle, as you can see. And such animal can maneuver very closely to obstacle thanks to its compound eye. You can see that the compound eye covers most of the head here. And so the compound eye also covers most of the field of view available around the head. So very recently in US, Robert Wood lab at Harvard managed to build such insect-scale flying robot. You know, it's very tiny robot, only 100 milligram, less than 1 gram, I mean 0.1 gram. And this robot is stabilized using external camera, and also thanks to some cable that bring the power and the control signal to the robot. But so this robot cannot fly by itself using its own sensor. It needs all this external camera. So the idea, if you want today to that such a robot can pilot by itself, is to bring some sensor on board. And to look for this new sensor to make on board, we look at insect, actually, at the compound eye, for example. And so the scientific method we promote is this biorobotics that take inspiration from insect, the insect compound eye, for example, and build, for example, biomimetic sensor, such as this artificial compound eye, the first ever programmable artificial compound eye that has been called CURVACE, and to use this onboard robot to test new principles that we are able to discover on the insect. And in a fair return, the idea is to put some new hypotheses toward biology to better understand how such animal work, such insect fly, so insect avoid obstacle, land precisely, or land even a swinging flower, and to even better take some inspiration to build even better robots, possibly. So here is the compound eye. You can see all the facets here of Calliphora fly here. So it could be, for example, 1,000 of facets here, 1,000 of facets on the left-hand side and right-hand side. And to simplify, behind each facet, there is only a couple of photoreceptors. So in total, it's not millions of photoreceptors. Here is a matter of 1,000 or 2,000 maximum photoreceptors. So if we simplify here the compound eye, we have, for example, the photoreceptor here and here that are coupled to a lens. So it makes, it's creating two optical axes that are separated, for example, by 2, 3, or 4 degrees, depending on the species and also the area inside the eye. And so in total, it's a very coarse resolution, very low resolution. Also, which is very interesting, is the acuity is not good also, because it's not a square sensibility, it's a bell-shaped sensitivity. So on the top of this very coarse spatial resolution, we have this blur effect on each pixel. So we take also inspiration of the ability to natural photoreceptor, for example, in the compound eye, to auto-adapt versus change in illuminance, change in the background illuminance. For example, here you have some work made by Laughlin in UK that give you some idea of the depolarization of a photoreceptor inside the compound eye in case in local change in luminance for many luminance from, for example, very dark adapted photoreceptor to light adapted photoreceptor. So it could be over, for example, 5-6 decade range. And in the lab, very recently, we managed to mimic such adaptation using a silicon retina. So this retina is not a matter also a million of pixels, but there is also only 12 pixels in this chip. So it's very low resolution. But each of these 12 photoreceptors well adapt to the background illuminance. So here is a matter of 1 lux to 100 and 1,000 lux. So 1 lux is about to be the night, and 100 and 1,000 lux is at summertimes nearby the pyramids, for example. And you can see that for all this background light, the photoreceptor will adapt to any change around this light that create a contrast. So for every change, the photoreceptor respond in the same way for all these decades. So to do what? And we need that, we think that if we want to measure the optical flow, this visual field of sweeping speed that you can see here on board this wingsuit jumper, you see this sweeping sweep underneath, on the right, on the left, and all this optical flow vector need to be measured independently from the background illuminance, even if you are in the dark or in the sunlight. So this is very important if you want to have robots to be able to go outdoors to have such a robustness to light change. And we know that this optical flow vector field actually is used by insects to navigate. And this vector field depends on the speed and the distance to the object. So also quite recently, we built, in the framework of a European project named CURVACE, the first ever artificial compound eye that is programmable. I mean, we can choose a region of interest inside this eye, and also we can use it on board robots. I will show that. So this compound eye is made of 42 columns, vertical columns, made of 15 pixels, 15 light-adapted pixels. So in total, we have 630 pixels, and the mass is below 2 grams, so it's very light sensor. You can see the euro coin behind, so it's a very small one, actually. The picture is huge, but it's a very tiny sensor. And the field of view is also very large. You have 180 horizontally, and vertically you have 60 degrees. So the field of view of this sensor is very nice, it's very large, but as I told you before, the resolution then is very coarse. The resolution of this sensor is only 4.3 degrees. Anyway, with such a sensor, we are able to measure the optical flow field, for example, in rotation, for the upper part, and in expansion, where we approach a wall for the down part. So I will show you some bio-inspired robot now. So we use this CURVACE on board a tethered robot. It's not a free-flying robot, it's a tethered robot that actually is a tandem rotor. So there is 2 rotors. So this robot can go up, can turn in pitch to go forward, and also turn in pitch. So we use two CURVACEs, two artificial compound eye back to back here. And we use some region of interest of this compound eye to measure the optical flow a bit forward underneath, a bit backward underneath, and also from the top. So we have 4 regions of interest where we measure the optical flow. And so thanks to this optical flow measurement, so you can see that the robot is avoiding it's very loady actually. Okay. It's enough, I think. Okay, so the robot is avoiding the terrain thanks to a ventral optic flow regulation. So it's using the measurement coming underneath to regulate the optical flow. And just by using the optical flow, this robot is able to follow the terrains. And you can see you have exactly the same behavior independently from the background illuminance. You have, for example, we saw 40 lux to 2000 lux. Actually, it would work also at 5 lux, but the picture, the video here will be completely black. So I don't want to show you a black video, or a completely white video. So I'll just show you the extreme that is still visible. And another principle that we look at for insect is that currently, actually, every air vehicle control its pitch and roll using the gravity. All the robots use inertial measurement unit. They are using, big gyroscope or whatever. And we notice that winged insect actually, they don't use the gravity as far as we know. And because they don't have any accelerometer. So we were thinking how to build a robot that will not use any accelerometer to try to understand how insects succeed not to fly with any accelerometer. So we use actually the same robot without any accelerometer, just using a ray gyro and this 4 field of view for the optical flow. And we apply some criterion on the optical flow to make it to follow, for example, the surface. And you will see that this robot actually fly quite well, but is not able to avoid, for example, very steep relief. To make it to avoid such very steep relief, actually we add another feedback loop here. Okay, so you will see it will crash again, and we add another feedback loop that actually orients in real time, all the time its head with respect to the local surface that is sensed by the optical flow. So by reorienting the optical flow sensor parallel to the local surface that is sent by the optical flow sensor by itself, we can make the robot to see much better this steep obstacle and still not to use the accelerometer. Okay, so we also disturb the robot using some pitch disturbance. And you will see that thanks to this reorientation mechanics of the head, there is a decoupling, a total decoupling between the sensory input and the control output of the robot. So the locomotion and the perception are completely decoupled, which facilitates actually the sensory motor control loop and the behavior for the robot. So then we'll see we disturb a lot the robot by moving the ground up and down, and to rotate it, and the robot managed to stabilize its pitch, control its speed, and control its height without any idea of the height, the speed of its orientation by only applying some optical flow criterion. So there is no distance sensor, no speed sensor, just optic flow regulation control loop, actually free control loop. So the robot doesn't know where is the deck, the speed of the deck, or whatever. It's just reacting when the floor is coming up, it's flying up. When the floor is coming down, it's flying down. It's decelerating when the vertical tunnel is coming to be too narrow by using this optical flow criterion. Okay? So I don't know if I'm running out of time. Another robot that we built, we took some inspiration from Srinivasan group in Australia. He trains bee in narrow tunnel, and we actually noticed that he noticed, that the bee in narrow tunnel are more or less center in a tunnel. They fly always center in the tunnel, and when we move one wall of this tunnel, the bee decenter, actually, they change their mean position toward the wall that is moving forward, for example, or against the wall that is moving backward. And so from this experiment, Srini said that bee normally show centering behavior, but for sure, actually, they do not react to distance from the wall, but only from the optic flow. Okay, just a last video to show you the robot. So thanks to, we did some experiment on the bee. Here, I would like to show you. We did some experiment on the bee to check somehow this data from Srini, and we find somehow that maybe the bee regulates also laterally the optical flow, and we built a robot, actually this hovercraft that mimic the behavior of the bee. You can see, for example, that this hovercraft, using only 4 pixels, 2 on the right, 2 on the left, is able to follow this wall and just here. Is also able, for example, to decelerate when there is a tapered tunnel. So this is a slow video, so it's a bit slowed down, but you can see that the robot decelerates, approaching this constriction point, and then accelerate automatically without any idea of the distance to the wall, just by measuring the optical flow on the right and the left. So in total, this robot mimics 7 behaviors that is well known on the bee. So, for example, in this tunnel, large tunnel, but also it mimics the fact that the bee keep the speed constant even if there is a wind head disturbance. Okay, I would like to thank my co-authors, and you can see where is the lab in the middle of the French National Park of Calanque in Marseille. Thank you very much.
Our next speaker is Dr. Nikolaos Mavridis. He is the founder and director of the Interactive Robots and Media Lab in United Arab Emirates University. We will show a recorded video about his presentation.
Imagine a world where robots are part of our everyday life, and not only as helpers, but as companions and friends. And furthermore, imagine a world where we can all take part in giant intelligent entities made up of potentially thousands of humans and machines, even if with a few seconds of our time every day. entities whose capabilities might well far surpass the current limits of both human as well as artificial intelligence. These have been my dreams and my goals in the last years, and they have indeed produced some fruit. In the words of the BBC regarding my lab, the Interactive Robots and Media Lab.
His name is Ibn Sina, named after the ancient philosopher renowned for his early scientific discoveries. But unlike his older counterpart, this Ibn Sina is altogether more high-tech. As well as being fluent in English and Arabic, he can hold a conversation with humans. He looks for information about us on the internet and uses that to chat with us. He'll also remember it for the next time you meet. But this lab isn't in Japan, China, or the United States. It's in Al Ain, just an hour's drive from the UAE capital, Abu Dhabi.
But however intriguing as this future world might be, full of robots, a very important question follows. How can we try to make sure that the building is closer to a world of harmony, progress, and peace, and not to a horrific dystopia full of suffering and destruction? This is the overarching question that I want to ask in my talk. And in order to explore this question, I would like to ask you to embark with me upon a journey that will consist of 4 stages. First, I will start by talking about the beauty of nature, and passing through the nature of beauty, I will arrive at the beauty of relations. Then I will talk about human-human relations and arrive at human-machine relations. And then we will change our topic of inquiry from the nature of the beautiful to enter the nature of the good, and thus discuss ethics. And finally, we will talk about roboethics and ask, can a machine decide on its own what is good and what is bad, and act and even kill accordingly? Are you ready? Yes. Let us start. The beauty of nature, manifested in all scales between the microcosm and the macrocosm, has always reflected upon us through a deeply rooted sensation of happiness, amazement, and peace. Proceeding, though, from the beauty of nature to the nature of beauty has always been a fascinating topic of inquiry. And for the ancient Greeks, who were lovers of art and humanity, beauty has often been equated to harmony, and harmony to proportion. But arithmetical proportion is just one form of relation between entities. And for the Greeks, harmony had a much wider sense. One could even define it as the perfect reflection of the relation of the parts to one another in the relation of the parts to the whole. And thus, one moves from the beauty of isolated entities to the beauty of relations, and from relations of abstract proportions to relations of living beings. And who would ever be left untouched by the warm reflection of the love of the last rays of the fall of humanity, embracing the first rays of the spring? But our world nowadays is not only full of living beings, we have machines everywhere. And recently, we also have a lot of intelligent machines around us. But how much has our life changed since the introduction of intelligent machines? Just think to yourselves. In the last week, how much time have you spent in direct interaction, one-to-one, with other people? Versus how much time have you spent in mediated interaction through your cell phone, through a chat server, with other humans? Versus how much time have you spent interacting with machines and not humans? The average American is spending more than 2 hours of his day online, and a big part of this time has to do with interaction with machines and not humans. Thus, we're spending more and more time with machines, and as a consequence of that, we're forming relations with them.
Where is the red one?
Most of my work had to do with human-robot interaction. Machines that could actually learn the meaning of words through examples, or form relations with humans by creating shared memories and shared friends, or even androids. They could have facial expressions, they could come into verbal conversation with humans, here in Arabic. And even show as well as recognize emotions. Here you can see sadness, disbelief. And finally, excitement. And all the robots that we'll be interacting with in the future might well be powered not by onboard processing power, but by massive distributed intelligence that will be human and machine at the same time, that might be actually be given to them through the cloud, as I have talked about in my previous talks. But the big question here is the following. Okay, some of these robots might indeed be friends and companions, and this is what we talked about before, and this is what we want to have. But how about robots that will become armed guardians or lethal enemies? How can we try to safeguard beauty and make sure that we don't enter a dystopian nightmare through the introduction of these machines? This is exactly where ethics enters the picture. And not just the normative, sterilized textbook ethics that you read about everywhere, what should be, but the actual real-world ethics, which is much more complex, what really is. And thus, we're moving from an inquiry of the nature of the beautiful into an inquiry of the nature of the good. But what is good and what isn't? Well, depending on which philosophical or theological viewpoint one takes, there's many possible answers. Of course, philosophy stems from logic and sensory experience, while theology in most cases from revelation and mystical experience. But again, still, what is good and what isn't? Socrates would tell you that knowledge is good, and especially self-knowledge. Aristotle would disagree, saying that self-actualization, turning every potentiality into actuality, is what we should be going for. And the Stoics, who had a different opinion with apathy, the Epicureans would talk about sustainable pleasure. And if we went over to ancient China, we would see the good moving away from the individual and entering the whole state, and thus the first conceptions of the common good being phrased. Then we could go back to the Middle East and have a look at the Abrahamic faiths, equating the good with following divine law, or with love, as it arguably is in Christianity, or submission to divine will. Or we could even get modern scientific theories, such as the ones that David talked about, who might equate the good in the end with evolutionary fitness. And if we go out on the street and ask people, they will tell you things such as, well, the good is money, the good is fame, the good is power. But however varied all these conceptions of the good might be, they are not unrelated with one another. And furthermore, nowadays, each one of us is free to choose whatever he wants, or create his own conception, or create an eclectic mix of all of the above. And no matter how much variance we have in the good, it's a good thing that we have a lot of agreement on what isn't good. Death, suffering, pain, slavery, cutting off knowledge from people are things that we all agree shouldn't be there. And this is why we were able to create foundational documents such as the Declaration of Human Rights, or the Geneva Convention regarding warfare, or even the first machine ethics declarations that have started to appear. But even if one decides what is good and what isn't, there is still a lot of space for adjusting priorities and parameters in the system. Just think to yourselves that you had the following dilemma. If you had to choose between the certain death of a child and the probable death of two adults, what would you choose and why? And thus we're entering our first question of roboethics. Can a machine decide on its own what is good and what isn't, and act or even kill accordingly? Well, killer robots are not anymore something that's just there in sci-fi. They're starting to get deployed in the battlefield. And soon we might also have human-robot hybrids with prosthetics, not really like Robocop, but getting closer to him, out there too. So what can we do? I mean, what are the conditions for granting to such a machine the license to kill? Well, there's at least three kinds of conditions. First of all, it should be able to make a correct decision before the action. Then, it should be able to shoot accurately and get implicated accurately during the action. And in the end, we should be able to assign responsibility after the action. Most people think that correct decision-making is just a matter of logic, but if you think about it, this is a very big fallacy. Behind every decision, there's three things. There is an implied or clear ethical system dictating what is right and what is wrong, what is correct and what isn't. There is information pertaining to the decision you're taking, and there is reasoning that has to be fast enough and deep enough. But who is better, humans or machines, when it comes to these three conditions? Well, ethical systems for machines arguably are there since the introduction of the famous 3 laws of robotics by Asimov more than half a century ago. However, they have proved to be quite difficult to implement in this form. But nowadays, there's recent research in machine ethics that enables us to really get AI programs that are able to create moral judgments and ethical decisions, at least beginning to do so. When it comes to information, what one really needs is situational awareness through video cameras and sensors, and also access to databases when he's in action. And there, humans have a disadvantage, which comes from the fact that they need an interface, and there is a bottleneck in the interface. And finally, when it comes to reasoning, although it might not be exactly true that human emotions always interfere with correct reasoning, the horizon of possible extensions of speed and depth in the reasoning of machines is much bigger. Thus, in conclusion, it seems that at least where we are right now, we cannot decide, but in the future, machines will have the upper hand when it comes to correct decision making. And they already have it when it comes to accurate shooting, where they have much superior sensory-motor capabilities and reflex times. But things are not so clear when it comes to responsibility assignment. I mean, just think to yourself. Imagine that you have an accident where a robot kills somebody who shouldn't. Who is there to blame? Can you blame the robot? Can you blame the manufacturer? Can you blame the owner, the programmer, the engineer, the trainer of the robot? Our legal systems cannot really give you an answer. Well, according to Anglo-Saxon civil law, if you think of the robot as an artifact or as a dependent person, then it is the guardian that gets responsibility, but he's always a human. But if you try to apply criminal law, then in order to be able to punish or to reform somebody for a crime, he needs to be considered as a moral agent. And robots nowadays certainly cannot be considered as moral agents. So only when we reach a state where robots might be able to pass some kind of a moral Turing test in which we will ask them moral dilemmas and we will get their answers and see if they're indistinguishable from humans or not, will we be able to potentially consider them as moral agents. Thus, although right now there is no clear superiority for humans or machines, I think that in the future, machines will be more capable for getting the license to kill. But does this mean that humans will be left out of the loop? Let's start again. But does this mean that humans will be left out of the loop? No, not at all. Humans will always be there to design machines, devise their ethical systems, tune the parameters of the systems, and then authorize, deploy, and supervise machines. And in many cases, we will always have some kind of mixed autonomy with both of them in control. Thus, having seen the first question, let us move to the second. How can we try to make sure that we can safeguard beauty and get closer to utopia and not a dystopia in the future? Well, I don't know the answer. And I don't even have a clear sketch of a possible answer. And that's exactly why I'm here talking to you. I do know, however, that any such answer should definitely pass from at least 3 things: delicate social engineering, opinion making, and tough politics. And there is an intricate web of actors and interests behind the situation. You have the governments of the world. You have the military industry, extremely powerful, and the IT industry. You have academia, with whatever role it might be playing today. You have the mass media and the opinion makers, the international organizations, and in the middle of it all, you have the citizens of the world that have the right to determine their own future. Within this situation, what we really need to do is to be able to find a way to do a delicate realignment of the interests, the roles, and the relations of all of these entities in order to start moving in the right direction. And there's many open questions in roboethics for which we neither have enough theory nor experience. I mean, will robo wars be shorter and cleaner than traditional wars? Will robots ever be considered as moral agents? How about cultural differences in the perception of robots? I mean, Japan is a very different place for robots when it comes, to the differences with Europe. One other important question, is waging ethical warfare a disadvantage to those that are waging it? And even more so, beyond killer robots, how about the ethics of companion robots, medical robots, and all the social robots that we talked about? I mean, would you let your child be taught by a robot? Would you let your baby be taken care of by a robo-nanny? And there's many questions around that. Therefore, we have gone a long way today, and I have gone a long way from the red spot, I guess. We started by talking about the beauty of nature and arrived at the beauty of relations, and we talked about human and human-machine relations. We talked about ethics, and finally robo-ethics, and asked what is required in order to give to the machine the license to kill. Humanity has gone a long way too. We were able to fight disease. We were able to conquer the skies and reach space. We were able to, up to a point at least, extend our lifetime and increase our population. However, as once General Omar Bradley said, we are still in many respects ethical infants. I personally come from a tradition that deeply values radical innovation, and thus I wouldn't want to see humanity getting back into a recession with no progress due to the fear of introduction of new technologies. When there is so much that we can do in order to improve the human condition and break through our limitations through technology. But at the same time, I come from a tradition that values beauty very much. And not only the superficial kind of beauty of form, but the deeper beauty of relation. And thus, I wouldn't want to see humanity pass through a horrific disturbance as a transitional phase due to the unthoughtful introduction of all of these new technologies. Thus, we really need to think deeply and devise social processes in order to be able to make sure that we can embed ethics in the introduction of our exponentially growing technologies. And this ethics has to be vitalizing and humanizing and not castrating and inhibiting. This ethics has to be safeguarding harmony and not hindering progress. Therefore, imagine a world that robots are part of your everyday life. And not only as helpers, but also as companions and friends. A world where the crippled get feet and walk, where the blind get eyes to see, where beautiful memories are retained forever. A world where, in the smart green cities of the future, our citizens can make their dreams come true through participatory processes, and we can safeguard the biosphere of our beautiful Mother Earth. And in order for us to be able, this dreamlike world, make this dreamlike world a reality and not a nightmare, this should also be a world where humanity will have remembered what it has often forgotten. That beauty lies not in the form alone, but in the relation. And that if one looks carefully and far away towards that infinitesimal point in the horizon, it is always true that the rays of the persistently and essentially beautiful converge with the rays of the good. Thank you.
Thanks for Dr. Niklaus for this interesting video presentation. Our last speaker is Dr. Victor Park, Assistant Professor, Waseda University, and Adjunct Professor at EJUST. Please.
Hello. Ladies and gentlemen, thank you for participating in the last session in robotics, especially in biorobotics. My name is Victor Parque. I belong to Waseda University. I am adjunct professor in Egypt, Japan University of Science and Technology. Basically, my research areas are artificial intelligence, design, and optimization. And the works I will present today are enabled thanks to the collaboration with Professor Miyashita at Waseda University, and also Professor Higashi and Professor Kobayashi at Toyota Technological Institute. The main topic of my talk is basically about curves and surfaces, especially aesthetic curves and surfaces. We have been listening in the previous talk some very beautiful and deep thoughts regarding the nature of beauty. So in my talk, I will talk about the nature of beauty, but the beauty of curves and surfaces. Basically, we find curves and surfaces in nature everywhere. You find curves in cars, for example, you have curves in buildings. However, if you compare the cars and buildings perhaps 70 or 80 years ago, you can see that there are almost no curves. Why do you think it happened? Some ideas? Hello? Some ideas? Okay, the question is, if you compare, for example, a design of a car 70 or 80 years ago, there are actually no curves in the cars. Why? Why we were unable to handle curves? Yes. Well, that's a very interesting question. Another idea. Oh, very interesting. Harmony ideas are coming. Oh, interesting ideas in efficiency. Any other idea? Yes?
I think we thought that sharp angles and right angles were better or more efficient or more beautiful than curves, maybe at that time.
There is an ideas on different in perception. Yes? Again, please.
I think it's related with aerodynamics.
Aerodynamics. Wow. Another field of research is coming in. Interesting. Any other idea? Well, I think we are going to continue. One of the main challenges in dealing with curves, especially aesthetic curves and surfaces, is the complexity of handling such kind of things. As Professor Shockley said, it's not so easy to compute with curves and surfaces. And 8 years ago, as you may imagine, we didn't have computers and not even calculators. How to compute such kind of shapes was not so easy to handle. But nowadays, you can see that, for example, BMW or Toyota are manufacturing very beautiful shapes, or perhaps there are architects who are considering very beautiful shapes in a building, because we are able to compute very efficiently using perhaps a complex calculator or complex computers. And basically, we find curves in nature, but we are unable to understand it very deeply. So one of our topics is how aesthetic curves and surfaces are formed and how they should be formed. A main concept in a beautiful curve is basically a minimum variation in curvature, and this variation should be as linearly as possible. I present these three cases, 1, 2, and 3. The top part is there is a monotone variation in the curvature. In the second case, the curvature variation is non-monotone. It's kind of perhaps quadratic. But in the third case, it's completely non-monotone. And there are actually two inflection points. We can see that the first case is actually one condition, one essential condition in order to build an aesthetic curve, a beautiful curve. Mathematically speaking, it's actually just, for example, if you can handle a piece of wood, just try to find a piece of wood and try to bend this piece of wood by the two axes. For example, you have the left and the right, you can build a very beautiful curve there. And this beautiful curve is actually a mathematical problem. You just have to minimize the bending energy. And the K1 here is the curvature of this curve. And if you minimize this equation, people say that you can obtain a beautiful curve. Well, in surfaces, well, we have two directions because a surface is just a collection of many curves in two directions. You can minimize this summation of curvatures along the two directions. So people thought it was very easy to construct beautiful curves and surfaces just by minimizing the energy. Especially people have focused on 5 types of energy functions. You can see in this slide, for example, the most common, the most popular ones. The first one is called the bending energy, and the last one is called the distributed load. You are going to see, if you are studying curves and surfaces, these kind of metrics in the literature, in the books. However, we are proposing a different idea. We are proposing that a aesthetic factor of a curve should be that the curvature radius should be as linearly as possible. And for a surface, since the surface is just a collection of curves and in two directions, we just have to assume all the aesthetic factors in two directions. So if we approximate this problem as an error minimization problem, we think we can obtain much better results compared to the conventional energy metrics. And we did some comparisons, for example, in 2D curves. The blue one is our case, and all the other colors are, in the left one, are the conventional methods. And I can see, for example, in the top rightmost part, the most important aesthetic factors for many different values of alpha. We are pretty sure that you may like one of these curves as a sign of beauty. And for surfaces, we have compared with the conventional methods, and we obtained that in our method is almost as efficient as the distributed load, which is, well, the most effective until these days. And we have made lots of comparisons. We have determined that the rightmost part is our method. You can see that the variation in curvature is just linear in both directions. So we have done lots of comparisons, and we have concluded that our approach actually leads to beautiful shapes. Not only to beautiful shapes, but also our approach is a little bit faster compared to the conventional methods. For example, just compare 100 seconds to 40 seconds. So we actually can compute the beautiful curves in almost real time. Of course, we are not using any GPU or graphics processing unit or any fast computer, just conventional computer. And we have been applying these kind of concepts in life sciences. For example, when we want to treat some organ in the human being, we want to predict what will be the variation of certain soft organs. So we can model the dynamics of any kind of soft organ just using the models of surfaces. Once we predict the paths of the motion, then we can perhaps we can predict where we can insert a needle, for example, or where we can cut as accurately as possible. And also, we have been trying to understand the laws of shape and motion in many different organs. For example, this is a lung system on a living organism, a real-world lung, of course. And of course, we are trying to, with the highest aim of performing the smooth surgical operations. Smooth means as safe as possible. You know that any kind of cut in surgical operations is a matter of life and death. And of course, since any kind of surgical operations is consisting of cuts or inserting needles, for example, we need the most precision in this kind of operations. And we are trying to do it in many small scale. Also, we are trying to study the membranes, especially the membranes inspired by origami, and we are trying to build those kind of shaped, beautifully shaped, foldable membranes. And we are trying to apply this one in medical applications, for example, to insert as a membrane, as a micromembrane on the soft body. And also we are trying to model some kind of ergonomics devices so that if we predict somehow how that change in the skin, for example, will happen, we can get a very precise model of the dynamics of the skins of the legs or any kind of part of the body, and then we can design much better ergonomics for assistive applications. Our highest aim is actually to build the conceptual methodology and tools in order to enable manufacturing of carved designs, not only machines, perhaps buildings, as fast as possible, and also to enable safe surgical operations. So I just gave a very brief introduction of our research topics in our university, so I'm very open to your questions and to your especially discussions regarding the beauty of curves and surfaces. Thank you very much.
Sorry, there is no time for questions because we are a little bit late and then there is a break now. So I hope that you will come again by 6 o'clock for the final sessions. Thank you.